pressure and the boiling point elevation, and then so. But you can see here, there's here we emphasize what this is non-volatile. Okay, the solute is non-volatile. Okay, the solute is non-volatile. This method for lab 3, I mean the solute is non-volatile. And then we can use this measure to measure the molar mass of a solid, which is non-volatile. And here there's another keyword. Here it said what? You may see it, may not pay much attention. This is called what? Non-electrolyte. So why we emphasize non-electrolyte? There's a reason. Okay, there's a reason. There's a reason. So this is non-electrolyte. Okay. And the reason is because the electrolyte can behave differently from non-electrolyte. As we discussed, colligative properties are proportional to what? The concentration of the solute particles. The particles. These particles could be ions, could be molecules, could be ions. So there are only two forms, right? If a material is dissolved, it either exists as what? As a molecule, or it either exists as what? Ion. So at a given concentration, electrolyte's effect on colligative properties is greater than non-electrolyte. Why is that? The reason is because, as you can see here, for non-electrolytes, dissolution of 1 mole of glucose results in 1 mole of solute particles. Why? Because glucose, when dissolved in water, still stays as what? Molecules. It's non-electrolyte. Glucose does not dissociate to form ions. It's organic molecule. They stay as a molecule. Like ethanol. When ethanol is dissolved in water, still ethanol molecules. Okay, molecules. These molecules, ethanol, the major composition is. So that is the formula of ethanol. So when dissolved in water, it stays as that. There's no ion formed. This molecule still exists, even though it could form, have been bonded with water, but it still stays as this molecule. No ions form. In contrast, 1 mole of sodium chloride, as we discussed, right? So when dissolved in water, sodium salt, 1 mole sodium salt, dissociate to release 1 mole of this sodium ion and 1 mole of chloride ion. So you can see the total number, or we can say the total moles of solution particles. You see that? Solution particles is 2 mole, right? So 1 mole sodium chloride can, when dissolved in water, can dissociate to form 2 mole of ions. So 1 mole sodium ion, 1 mole of chloride ion have 2 moles. Then the molarity doubles, right? The molarity doubles compared to the 1 mole of glucose. Compared to 1 mole of glucose. Okay. You see, we talk about the concentration of solute particles. These particles could be ions, could be molecules. For electrolyte, they can dissociate to form ions. Therefore, the concentration of solute particles is larger than those non-electrolytes under the same condition, because non-electrolyte cannot dissociate. Non-electrolyte stays as molecules. That's the reason we need to discuss at the beginning, what are electrolytes. Because they are different. Not only electrolyte can conduct electricity, while non-electrolyte cannot. At the same time, they can also cause different colligative, they can have different effect on their colligative properties. Van Hoff factor. Okay, Van Hoff factor. So Van Hoff factor refers to the ratio of solute particles in solution to the number of formula units dissolved. So predicting, for theoretically, you see, if we have 1 mole of sodium chloride, so this is what? This is the number of mole unit, right? 1 mole of unit. And then in solution, we have 1 mole of sodium ion and 1 mole of chlorine ion. Then the Van Hoff factor I equals what? The ratio of solute particles in solution, which is 2 mole, right? Here we use this as one example, versus the number of formula unit, which is 1 mole, because this is sodium chloride, and 2 mole is sodium ions plus chloride ion. This equals 2. Okay, that's a theoretical value. That is the theoretical value. For strong electrolytes, the experimental Van Hoff factors are always smaller than the theoretical value due to incomplete dissociation. What does this mean? Here, you look at this scheme, right? Even though potassium, this is chloride. Can you see it clear? Oh, you can see it clear. This is chloride. This is potassium ion. Potassium chloride is like sodium chloride. It's a strong electrolyte. Okay, it's ionic compound. It's soluble. For any ionic compound, if they are ionic compounds, and if they are dissolved, then they will form. They are good electrolyte, as long as they can be, as long as they are soluble. But for some ionic compounds, they are not soluble. When they are not soluble, they cannot dissociate to release ions. As you can see here, because potassium ion is positive, chloride ion is negative, so the attraction, this attraction is quite strong. It's quite strong. Therefore, they cannot dissociate 100%. They cannot be separated from each other 100%. They still have some kind of what? Ion pair. Okay, ion pair. See, when there's ion pair, they consider as what? How many particles? 1, right? If they're separate, this one, this is also ion pair. So this one and this one are separated from each other. They are considered as what? 2 particles. But this one is a pair, then this pair is considered as 1 particle. So in theory, this Van Hoff factor is 2, but in reality, still some amount of sodium ion and chloride ion stay together because of the strong positive-negative interaction. And you can check, so not much different. It could be 1.9. It depends on the concentration. Because if the concentration is very concentrated, right, then the more and more percentage of sodium ion and chloride ion can stay together. If the concentration is very dilute, then the water, there are many water molecules that can separate sodium ion and chloride ion. Okay. And the effective concentration, that's what we call effective concentration, known as activity, is smaller than predicted ion concentration. So here, the ion concentration we predict, here we 1 molar, 1.0 molar solution, right? And we predict the concentration of ions, including both positive ion and negative ion, 2.0. But in reality, it could be 1.9 or 1.8, 1.95, something like that. So And then this is called effective concentration. Effective means this concentration can lead to qualitative properties and affect qualitative properties. Okay, so here we have work on question 54. We here arrange the following solution in order by their decreasing freezing point. Decreasing freezing point. Here we need to first, you see, here we need to first figure out the what? Their effective concentration or activity. Effective concentration. So what's the effective concentration for 0.1 molarity sodium phosphate? So for sodium phosphate, right? This is an ionic compound, right? For any compound with sodium ion in it, it's ionic compound. For any compound. Okay, for any compound, it's ionic compound. And then remember, in chapter 4 we discussed for any salt with sodium ion in is soluble in water, right? Remember, we discussed this. For any compound with sodium ion, it's ionic compound. And for any compound with sodium ion, it's soluble in water. It's soluble in water. Then, when it's dissolved, so we got this 0.1 molarity. Then what's the concentration for sodium ion? Because molarity equals what? Mole of solute divided by what? By the kilogram of solvent. When